Thank you, Professor Kim. Can you hear me? Yes. Okay. Today I would like to describe not Interstellar and not the books I've been writing, but my current research, the things I have been thinking about and working on in the last few years. This is called geometrodynamics, and I will explain what that means in a few minutes. I apologize that I cannot speak Korean, but that's the situation, so I will speak English. I'm told that you can all understand if I speak slowly, so I will try. Let me begin with a black hole, because a black hole is the first and most important example of geometrodynamics. Black holes are not made from matter. Even though a black hole is created when a star collapses, the matter from which that star was made has long been lost. It was destroyed at the center of the black hole in the singularity. And the object left behind, the black hole, is made from warped space and warped time. And let me explain what that means. If I take an equatorial slice, an equatorial surface through the equator of the black hole, the geometry of that surface is not flat. If I take that out and I place it in a flat space that has 3 dimensions, in order to preserve the geometry, it will have to bend in the manner that I describe here. In particular, the circumference around the black hole is small compared to the diameter. It's a very long diameter, a very short circumference. And in that sense, the space around a black hole is warped or curved. As a physicist, I think of the higher dimensional space in which it is curved as a hyperspace that is not part of our universe. It's also sometimes called the bulk by physicists, a higher dimensional space in which our universe might live. At the center of the black hole, there is a singularity, which I may talk about at the end of the lecture if there is time. But it's a place where the matter from the star that created the black hole is the place where the matter was destroyed at the center of the black hole. Now, the thing you know about black holes, the most popular thing about black holes, is that if something falls in, it cannot get back out. So I imagine myself falling into the black hole. Now I'm a 2-dimensional Kip. I live on the surface here because the 3rd dimension is not part of our universe. I removed 1 dimension in order to discuss this. As I fall in, I send back a signal to you by microwaves. And they come out quite happily, and they tell you what I am seeing until I cross the horizon. The surface of the black hole is called the horizon. And once I'm inside the horizon, I and the signals get pulled downward toward the singularity. And neither the signals nor I can get back out. And I will explain why in just a minute. The usual description is that gravity is so strong that I cannot escape it. But there's a much deeper description of the reason for this that I will give to you. Now, the black hole has 3 forms of warping or curvature of space and time. First is the warping of space itself, which I have already described. Circumference small compared to diameter. The second is that time slows down near a black hole. If you were to be just above the horizon and you hover there, stay there, and for 1 hour, you may come back to Earth and 1 million years have passed. In the movie Interstellar, there is a planet called Miller's Planet that is outside the horizon, orbiting around and around. 1 hour on Miller's Planet is 7 years back on Earth. And that is the basis for much of the emotional story in Interstellar. Inside the black hole, time actually flows in a direction that you might have thought is a space direction. It flows away from the singularity away from the horizon toward the singularity. And the result of that is that nothing can get out because nothing can travel backward against the flow of time. If time travel is possible, it's only possible by going out in space and returning before you started. You cannot stay here and move backward in time against the flow of time. And because time is flowing toward the singularity, if you're inside the black hole, you are dragged by the flow of time away from the horizon, and that is the real reason nothing can get out from inside a black hole. The third aspect of the warping of space and time is the whirl of space. Black holes generally spin on their axes just as the Earth spins. And as a black hole spins, it drags space into a whirling motion like the air in a tornado. The closer you are to the horizon, the faster the motion of space relative to distant stars. So just as the angular velocity of air in a tornado is lower at large distances than it is in the core, similarly, it's lower at large distances for the whirling motion of space than it is at the horizon. So those are the three aspects of space-time warpage. They will all three play an important role in my talk. Now, it's interesting to ask, what is it that warps space and time this way? Since there's no matter at all, it's all been lost in the singularity. The warping is not produced by matter. It's not produced by the mass or the energy of matter. There is no matter. In fact, it turns out that the warping is produced by the energy contained in the warping. If you imagine taking a rubber sheet, a child's trampoline, you push on the sheet, you have to push with large force to bend the sheet. You warp the sheet, you change its shape, but you have put energy into the rubber, potential energy into the rubber that you have warped. If that energy is big enough, that energy of warping is big enough, that will produce warping or curvature according to Einstein's relativity. And so in that sense, the energy is contained in the warping. Black holes are held together by nonlinear self-interaction. The nonlinear interaction in the sense that their warping carries energy which produces the warping in a manner described by a nonlinear differential equations, Einstein's equations. Now, in 2006, when I began work on this topic, we knew a lot about quiescent black holes that are just sitting here spinning around and around. We knew the theory of those. It was described by something called the Kerr metric, and we understood that very well. We had never ever seen such a black hole, though we had already some indirect evidence for the existence of such a black hole, for example, in the center of our galaxy. But more interesting to me was a colliding black hole, two black holes that collide, and we knew nothing about how the warped space and warped time would behave when two black holes collide, and we had no observational data. It's as though you had seen the surface of the ocean on a very calm and quiet day. That's rather like a quiescent black hole that is just sitting here spinning. You had never seen the ocean in a storm. You had never seen breaking waves driven by wind as they approached the shore. And you had just no knowledge of that either theoretically or observationally. That's where we were in 2006. We just knew nothing about how space and time behave in a storm. The collision of two black holes is a storm. It creates a storm of large, very large oscillations of how fast time flows, very large oscillations in the shape of space and the whirl of space. And I wanted to understand how these things behaved and whether there was any interesting behaviors that we could discover here. This is what is called the nonlinear dynamics of curved space-time, or geometrodynamics. And it involves some of the deepest questions about the nature of space and time. Some of the most interesting astrophysical phenomena involve this kind of geometrodynamics. John Wheeler, who was my PhD mentor in 1962 to 1965, long, long ago, he invented the word geometrodynamics to describe this subject. This is a photograph I took of him giving a lecture about the subject. You can see his beautiful blackboards. We had no computers, no personal computers in that period. We had no PowerPoint, no Keynote. And so Wheeler would draw his pictures and equations on the blackboard. And he was the person who inspired me to be interested in geometrodynamics. But the problem was that in that period, we had no way to get any answers. We were not clever enough, not smart enough to solve Einstein's equations to learn about this. They were much too complicated. We did not have numerical tools for solving this. The computers were not fast enough, and we had not developed the right form of the equations for doing it on computers. And we had no hope to make any observations. So this subject remained dormant. Nothing was done on it until about 2006. And that's when my story begins. And the first breakthroughs came from numerical simulations, numerical relativity. Toward the end of the talk, I will describe the LIGO project, which Professor Kim briefly mentioned. One of my motivations for the LIGO project was geometrodynamics. So I wanted to be able to solve Einstein's equations on computers in order to study collisions of black holes so we could predict the gravitational waves, which I will describe, produced by colliding black holes. So we could use that in analyzing the data to look for these waves, these gravitational waves. So we could analyze the data and to figure out what's happening when the gravitational waves are produced by colliding black holes. So my motivation came from future observations with this LIGO instrument. And that motivation led me in the year 2000 or 2001 to start a research group at Caltech where I work, working in numerical relativity. Many other groups were already working in the subject. My special interest was to study geometrodynamics. So in collaboration with a group at Cornell University led by a former student of mine named Saul Tukolsky, I built a research group working on this. And the first successful simulation of colliding black holes was by one of our postdocs, a postdoc named Franz Pretorius. So the techniques for numerical relativity have been under development since the 1960s. The first big success was in about 2006. And this now is beginning to teach us about geometrodynamics. And my role has been to provide vision, suggest calculations to be done on the computer, and try to extract the information, understand what the computer is saying about geometrodynamics. Now, let me talk about black hole collisions. These, in fact, are the most violent events that occur in the universe. If you have two black holes, they orbit around each other, they collide, they merge, they produce a very large burst of gravitational waves that go traveling out through the universe like waves on the ocean or on a pond of water. The total power output, the luminosity in gravitational waves, during the collision is 10,000 times larger than the total luminosity of all the stars in our universe put together. 10,000 universe luminosities. It's unbelievable. It's 10,000 times brighter than all the stars, all the galaxies in our entire universe But all that power is coming off in gravitational waves, not in light, not in electromagnetic waves. And it is rather brief. For the black holes that we will study with LIGO, this burst lasts for about 100 milliseconds, about a tenth of a second. So it's a brief but extremely brilliant burst of waves. And there are no electromagnetic waves emitted at all, except if the black holes are surrounded by a disk of hot gas, a so-called accretion disk. Then in the collision, these waves going out and the energy they carry will disturb that disk, and there will be some bright electromagnetic emission, light, X-rays, gamma rays perhaps, and much later radio waves. But they're not coming from the black hole, and the luminosity is very, very small compared to the gravitational waves. The details of the collision, the geometrodynamics that I want to understand, these are encoded in the waveforms of the gravitational waves. The waveforms that look like this, that's the kind of waveform you might see for sound on an oscilloscope. If you speak into a loudspeaker and make a sound, create a sound wave image on an oscilloscope, that's the kind of wave I'm talking about. And just as my voice carries information carried by these sound waves, similarly, the gravitational waves from colliding black holes carry detailed information about geometrodynamics, which we want to extract by observing these waves, measuring the waveforms, and comparing with simulations on supercomputers. So let me show you one of the first successful simulations of the collision of two black holes. This was done by the group that I co-founded together with my colleagues at Cornell. It has now been expanded to include the Canadian Institute for Theoretical Astrophysics. The leaders at the time that this simulation was done were Larry Kidder, Lee Lindblom, Harold Pfeiffer, Mark Scheel, Saul Tucholsky, and then approximately 10 other young numerical physicists, mathematical physicists working on the computer. The movie I'm going to show you was made by Harold Pfeiffer, who now leads the group in Canada. So in this movie, you will see three parts. Up high, you will see two black holes, one here and one there, as you might see them if they were in front of a blue sky. Is that bright enough for you to see? Is that clear enough? No. Down at the bottom, you see the gravitational waveform produced by this in-spiral and merger. In the middle, you see a picture showing looking in from the bulk, from the higher dimension. You see the equatorial plane of these, the orbital plane of these two black holes. These black holes are not spinning, so they're very simple black holes, and they are identical black holes, not spinning, which is why this waveform is so very simple. And the color encodes the slowing of time near the black hole. The shape is the shape of space, and the white arrows are the motion of space relative to distant stars. In this case, motion produced not by the spin of the black holes, because the black holes are not spinning, but by their motion, they're traveling around each other. And let's just let the movie go. You see the two black holes up here at the top. You see the down here as seen from the bulk. When they get much closer together, I'm going to jump over to very late, because this gets boring after a little while. So I jumped over. Now we will watch them collide. At the moment of collision, we will stop the movie so you can admire it. And then we will let it finish. And this is the result of one of those first simulations. It was the first movie that was made by these simulations a few months after Franz Pretorius had his big first success with simulations. Now there was a problem with this movie. It contains much too little, much too small amount of the information about the space-time geometry. It just contains very little of that information. And so when these successes had been made, and we were now doing many simulations quite easily, I got together a group of students at Caltech, myself, I think this was 2011 we published this, so I had now retired. I was no longer mentoring students. These are the students of Yanbei Chen, who took over from me as one of the new leaders of my old research group. And Jean-Drew Brink, a brilliant young woman in South Africa, who was another of the leaders of this collaboration. And what we did was we invented a new way to visualize the curvature of space-time. I'm now going to get, in a moment, I'm going to get a little bit more technical than I would like, but I want to describe the underpinning for what I'm doing in a moment. First, I'll give a simple description of the first part of this new way of thinking about things. Let's begin with a quiescent black hole. In technical language, a Kerr black hole. It's spinning on its axis. And imagine placing a physicist near the north pole of this Kerr black hole. She looks down at her feet. Let me start over, be a little more careful. As the black hole spins, it drags space into motion. Technically speaking, what really is happening is inertial frames are caused to move. That means that a gyroscope, which tells you about inertia, a gyroscope, which would normally just point at the distant stars, it turns around and around because the black hole is spinning and it is dragging space into motion, is the way I describe it in an elementary description. And so if she has a gyroscope at her feet and one at her head, and she looks at how the precession, the turning of the gyroscope at her feet compared to the one at her head, it may turn rather rapidly around and around in a counterclockwise direction. If you think about it, the gyroscope at her feet, if it looks at the gyroscope at her head, that one up there also turns in a counterclockwise direction. You can see this yourself if you take a wet towel full of water and you want to twist the water out of it. You turn your hands to twist it. One hand will see the other go counterclockwise. This hand will see that one go counterclockwise. So it's a counterclockwise twist. There's a counterclockwise twist up here. If the angular velocity of that twist is proportional to this physicist's height. And so if I take that angular velocity, I divide it by her height, I get a number that is independent of how tall she is. This truly characterizes the twisting of space at the north pole of the black hole. And this is what we call the horizon vorticity. The horizon is the name of the surface of the black hole. It's vorticity. It's an analog of vorticity of a fluid in fluid mechanics. But in this case, it's a vorticity, a twisting of space or of inertial frames. Similarly, the south pole, if you think about it, you see that there will be a clockwise vorticity similarly. So you have a counterclockwise vortex in some sense at the north pole and a clockwise one at the south pole. The region that has high vorticity we call a vortex. And so there's a counterclockwise vortex in the horizon of a black hole at the north pole, a clockwise vortex at the south pole. And there is a number for the strength of this vorticity that you can work out from the equations of general relativity. Now, what happens outside the black hole? This is where I will get technical, but only a small portion of you will understand this. The rest of you can get some rough feeling for what I'm talking about, but I think it's useful to describe in some precise way what is happening. In relativity, space and time are unified into a four-dimensional space-time, and we find it useful to take a three-dimensional slice or surface in four-dimensional space-time. We call that space, and it's our choice as to which slice we take and call our space. But once we have made that choice, a quantity that's called the electromagnetic field tensor breaks up into two pieces, the electric field that is familiar to all of you and the magnetic field that's familiar to all of you. And we visualize these in ways that most of you know about. we visualize them by field lines. If you have a positive electric charge and a negative electric charge, electric field lines go from the positive charge to the negative charge like that. And that's how you visualize in your mind or on paper electric field lines. And similarly, the magnetic field lines around the Earth, that the dipole magnetic field of the Earth describe the magnetic field. Now, in relativity theory, the curvature of space-time is embodied in something called the Riemann curvature tensor. And in vacuum, if there's no matter around, you can split this up into two parts, similar to what you do for electromagnetism. They're called the tidal field and the frame drag field. And these are mathematically, they are second-rank tensors that are symmetric and trace-free. So that's what they are mathematically. Again, for the experts, if there is matter present, we remove the traces of the Riemann tensor and work with a so-called Weyl tensor, and everything that I described goes on through. And so the tidal field is the thing that stretches you and squeezes you if you are accustomed to those ideas of what happens, for example, near a singularity. And the frame drag field is the thing that produces this precession of gyroscopes. And we can visualize both of these by a network of field lines, the same way as we do in electromagnetism. So what these students and I have done is to discover a way to draw field lines that describe the tidal fields that stretch and squeeze and the frame drag fields that twist space, just by field lines like we use in electromagnetism. We call these, for the frame drag field, we call these vortex lines. And these vortex lines are integral curves of the eigenvector field so let me start over again. The frame drag field is a second-rank symmetric tensor. You can think of it as a matrix. It has eigenvectors. And the so-called integral curves of those eigenvectors are the vortex lines. And the eigenvalues are the vorticity. So that's the mathematical basis that is just much more complicated than I would like to describe, but I would like you to know what the underpinning for this is. So these are these field lines, the analog of magnetic field lines. They're the vortex lines around a spinning black hole. And so to return to my earlier description, if I look at this blue vortex line, and I place my physicist along that blue vortex line, when she looks at her feet are moving clockwise relative to her head, or a gyroscope at her feet is moving clockwise. Her feet look at her head, the gyroscope at her head is moving clockwise. The ratio of the angular velocity that is seen divided by her height, again, is a number, and it is this vorticity, which the eigenvalue associated with the integral, with this integral curve, with the eigenvectors that are parallel to that integral curve. And so we have everywhere we have a vorticity. Along this direction, she is twisted in a clockwise manner. Along that direction, she's twisted in a counterclockwise manner. The red lines are counterclockwise twist, and the blue lines are clockwise twist. A region where you have very high vorticity, we call a vortex. And so sticking out of the north pole of the black hole, there is a vortex that is counterclockwise, a large counterclockwise twist all the way along here in that direction. Sticking out of the south pole is a clockwise vortex. So that then is the underpinning for what I'm going to tell you, and I'm going to be talking about these two vortexes or vortices, a counterclockwise one and a clockwise one, which stick out of a black hole. So if I just back up for a moment and say it now more simply, when a black hole spins, it has a vortex of twisting space that comes out of its north pole, and it twists things in a counterclockwise way. A vortex sticking out of its south pole that twists space in a clockwise way. And these vortices are a part of the warping of space-time that nobody knew about until we began to do this work, motivated by these simulations. So now I will describe a simulation where the team I work with took two black holes spinning and made them collide head-on. This black hole has a blue vortex sticking out of its north pole and out of the upper pole, a red one out of the lower pole, counterclockwise, clockwise. This one is oriented in the opposite direction. And so they will collide with each other. And down here you see the red horizon vortex and the blue horizon vortex, out of which these vortex lines emerge. We will watch the beginning of this simulation, and we see the horizons merge. I began with two black hole horizons. These are the points of no return. You fall through there and you can never get out. They have collided, merged. We now have a single horizon. But whereas before the collision, you have one red vortex and one blue vortex on the black hole, you now have two red vortexes, one here and one down there, two blue ones here, one here, and one down there. So now you have a black hole with four vortices of twisting space sticking out of it. And remarkably, these vortices are very robust. They retain their individuality basically forever thereafter. But they die gradually in a manner that I will describe. And so I'm now going to show you the entire collision of these two black holes. And I want you to watch, after the merger, put your eye on one of those vortices and watch what happens to it after the merger. So the black holes come in, the horizons have merged. That vortex was blue originally, now it's red, now it's blue, now it's red, but it's getting weaker. Now it's blue and very weak. It's still there, oscillating between blue and red, but it's so weak that you can't see it. So what's happening? What's happening is that these vortices don't like each other. In some sense, they fight with each other because they are twisting in opposite directions and they're side by side. And as they fight with each other, they exchange vorticity. The red one gives its red vorticity to the other one. The blue one gives its blue vorticity to the other one. The vorticity is oscillating back and forth. However, if you watch more carefully, you realize there's always a period when this horizon is painted green in between oscillations. And when that is happening, there are no vortex lines sticking through the horizon at all. So when they are starting to switch vorticity, the vortex lines have come off of the horizon. And so this shows more precisely what's going on. At the moment when the vorticity is strong, this vortex line is now coming out of the horizon, goes around and goes back in the horizon there. The two red vortex lines that came off of separate black holes, they have grabbed each other, they have linked onto each other and made a single red vortex that reaches out around and back in. Just to remind you, this vortex is like the twisting water in a bathtub, in a vortex in the bathtub. It's like the twisting air in a tornado. But now you have this twist that is emerging from one location on the black hole, going back into another location. A real structure in space that is part of the space-time curvature. It's an object that has now become rather complex, that's not made from matter. It's a complex object made from warped space and warped time. And these vortexes are a big part of that. Now, when this goes green, the red vortices have come off of the black hole, and they have to do something. They can't just end. They join onto each other, and they make a loop that looks like a smoke ring. And this is not drawn by an artist. This is from the computer simulations. This is a precise description of these vortex lines coming off the computer simulations in this very same black hole collision. And a blue vortex here. So these two vortices have come off the black hole. But when they come off, they kick back at the black hole in a form of radiation reaction, very similar to firing a gun and it kicks against your shoulder. When they kick back at the black hole, they recreate clones of themselves with vorticity reversed. And so that's what happens is a new set of vortices is put onto the black hole with reversed vorticity when these two come off. And so it's rather miraculous. This is what comes out of the simulations. Having seen this in the simulations, we have been able to go in and use perturbation theory for black holes and show that this happens analytically. In the case when the oscillations have become quite weak, we can do a full analytic analysis with the equations. But we had to see it first in the simulations. As these vortices go away from the black hole, they actually become the gravitational waves that LIGO, the project that I helped begin, is trying to discover. And part of what happens is these moving vortices, just as a moving magnetic field generates an electric field through electromagnetic induction, so a moving vortex line of twisting space generates a tidal field that stretches and squeezes. There are what we call Tendex lines that stretch our physicist if she is lying along a Tendex line, squeeze her for Tendex lines going in the opposite direction around and around this ring. So, and those are induced by the motion of the vortex lines by an induction process that mathematically is almost the same as what you see for an electromagnetic field, a magnetic field generating an electric field. Far from the black hole, these Tendex lines then have a stretch and a squeeze that are opposite to each other. So here's a squeezing Tendex line, and there is a stretching Tendex line. And those are the things, let me just go back, those are the Tendex lines that will drive the gravitational wave detectors in LIGO that I will describe in a few minutes. Just to make this more complete, in the more realistic case where the black holes are orbiting each other and merge, instead of oscillating back and forth in vorticity, the vortex lines get stretched out like water from a turning sprinkler, or like the spiral arms of a galaxy. And as the black hole spins, these vortex lines are dragged behind and become gravitational waves traveling out into the universe. I'm going to show you a simulation of a black hole with a neutron star. The black hole is spinning around this axis. The neutron star is orbiting in that orbital plane. The black hole is 3 times heavier than the neutron star, but only a small amount larger. As these go around each other, they will create gravitational waves in the same manner as for 2 orbiting black holes. But that's not the thing that interests me. What interests me is that the tidal force, the stretching and squeezing force from this black hole, the so-called Tendex lines from this black hole will tear the neutron star apart. And then the vortex lines from the black hole, from the frame drag field, will throw the neutron star of matter up in the air, so it's in this plane perpendicular to the spin of the black hole. This again is a simulation by our Caltech-Cornell collaboration. And this is what the simulation shows. So the neutron star is already starting to be thrown up in the air perpendicular to the spin of the black hole. It's been torn apart. The matter is falling into the black hole. About 15% of the matter is left behind in a disk of hot gas. and about 85% in this simulation has gone down the black hole. But the vortex lines and the Tendex lines from the black hole have torn the star apart. This is a star made of nuclear matter, weighing as much as the sun, 1.5 times what the sun weighs. Been torn completely apart, then thrown off in a new direction by the combination of these Tendex lines that stretch and tear the star apart, and the vortex lines that twist space and throw the matter in new directions. So it's rather remarkable how powerful this vorticity and the tendicity of stretching and squeezing are. This is the foundation for what we call multi-messenger astronomy. We will see gravitational waves from the orbiting motion and the collision. We will see gamma rays and neutrinos from the very hot neutron star matter when the star is thrown apart. And so we will do simultaneous observations to see all these forms of radiation and understand what happens when a black hole tears apart a neutron star. The gravitational waves, then, as I said before, are a way of probing the warped side of the universe. And this was my original motivation, except for John Wheeler telling me you should study geometrodynamics. How do you detect these gravitational waves? Here's a simple analogy. Suppose that you want to detect passing water waves. You live on the surface of the water. You're a small insect that lives on the surface of the water. We call them water skeeters in Logan, Utah, where I grew up as a small boy. And I used to play with water skeeters on the irrigation canals. These are very brilliant water skeeters. They have studied at Women's University, and they understand engineering really well. And so they build a detector to study the motion of these waves. They put 2 corks on the water. And you know when a wave passes, as you know from being in the surf in the ocean, it does not only go up and down, water goes back and forth. You're pushed toward and away from the shore. So these corks are pushed toward and away from each other. And you can obviously use a laser beam to measure those motions with high precision. The same kind of technique as it's used for surveying with laser beams. So we use then laser beams to look for gravitational waves. We have 4 mirrors that hang from overhead supports. When a gravitational wave comes along, it pushes these 2 apart because they're stretching in this direction, the Tendex lines from the gravitational wave. Those are pushed together by the squeezing Tendex lines. And then the stretch and the squeeze is oscillatory, and that is the waveform that I showed to you, the gravitational waveform, is the pattern of stretching and squeezing. And so the gravitational waveforms are what we compute in our simulations of colliding black holes. If we begin with 2 black holes that are identical, orbiting each other, but their spins are oriented like that, it turns out the waveform is a very interesting waveform. This modulation is due to the vortex lines from the spins of the black holes grabbing the black holes and making the orbital plane change as they orbit. So the gravitational waveform brings full information about what's going on with the spins of the black holes and ultimately about the collision. We are now carrying out about 1,000 simulations with black holes that have different orientations of their spins, different magnitudes of spins, different ratios of sizes or masses, in order to be a foundation for analyzing the data from our gravitational wave detectors. Returning to the detection process, the motions that we see will have, we expect, an amplitude less than 4 × 10⁻16 centimeters. Now, let me just point out to you what that means. Even for a 75-year-old physicist like me, it's useful to remind myself what 4 times 10 to the minus 16 centimeters is. In order to see these waves with confidence, the noise in our detector must be less than 1 times 10 to the minus 16 centimeters. Okay. In reality, with advanced detectors today, we are working at 1 times 10 to the minus 17 centimeters. But I'll talk about the previous generation of detectors, what we have done, the foundations for our past observations. You begin with 1 centimeter. For an American audience, I tell them that's about a half or a quarter of an inch, but you all know what a centimeter is. You begin with 1 centimeter. You divide it by 100, you get the thickness of a human hair, 100 microns. You divide by 100, you get the wavelength of the light that we use in LIGO, about 1 micron. And we use interferometry. I didn't say this, but obviously we use interferometry with light beams in order to measure those motions. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of the nucleus of an atom. Divide by 1,000, you get the noise level in our previous generation of detectors. Now, this is incredible that experimental physicists have built detectors capable of measuring motion of what are now 40-kilogram mirrors at a level 10 times better than this. It's just totally incredible. It's so incredible that when I co-wrote with John Wheeler and Charles Misner a textbook called Gravitation many years ago, I wrote an exercise in this book, and you can go read the exercise, which says approximately like this. It says, show that anybody who thinks they can build an instrument that will do this is crazy. And I then spent most of my career helping the experimenters do this, because I was stupid. I did not understand what fabulous modern technology is capable of. So we now have LIGO, the Laser Interferometer Gravitational Wave Observatory. It's a collaboration of, well, it's now 900 scientists at 75 institutions in 13 nations. This includes Korea. There are 5 universities or research institutes in Korea that participate, each with several physicists involved. It's based at Caltech because Ronald Drever and I, who started the project with Ray Weiss, were at Caltech. It's directed now at the present time by David Wrightsey. Gabriela Gonzalez is the spokesperson for the collaboration. And we have instruments in Hanford, Washington, and Livingston, Louisiana. These are vacuum pipes with laser beams going down inside the vacuum pipes. The vacuum pipes are 1.2 meters in diameter, 4 kilometers long. They are the largest hole in the atmosphere that I know of that the people have created. And inside there, the laser beams go back and forth, making these measurements, and also in Livingston, Louisiana. And we are planning to place one in India. And this is in the late stages, final stages of getting approval from the new government in India. It had approval from the old government, but when there was a change of the ruling party, it had to go through the approval process once again. And we, with these instruments, look at gravitational waves from what I would call small black holes in distant galaxies, masses between 10 and 1,000 times the mass of the sun, 10 to 1,000 kilometers in size. We look for waves from many other things, but for me, it's these colliding black holes that are interesting because those are the ones that produce geometrodynamics. So we have, in terms of a world map, then we have instruments now operating in Hanford, Washington, advanced instruments now operating in Hanford, Washington, Livingston, Louisiana. There is a Virgo project with instruments that will go into operation in several years. It's a collaboration of France, Italy, and the Netherlands. And then we have a test bed instrument for developing advanced technology that's part of the LIGO project in Hanover, Germany. And we have a huge, very large participation from Germany and from England in LIGO, and much of their contribution is this instrument on which we develop the next generation of detectors while we operate the current generation. Then also there is an instrument called CAGRA being built inside a mountain in Japan, and we are planning to put one LIGO instrument in India. So this is a worldwide network, all collecting the data, all the data coming together and being analyzed jointly among all the people around the world who work in this field. Because the noise in these instruments is sufficiently dangerous that we will not believe anything we see unless several instruments see the same signal. And we need several instruments in order to find the direction to a source by the delay in when the signal arrives at different locations on Earth, and in order to then extract the waveforms with confidence. We actually proposed building LIGO in 1989. I began laying a vision for this field around 1971. The experimental work, foundations for this were begun by Drever and Weiss and a group in Munich, Germany, around 1971. We actually were ready, the technology was sufficiently advanced to propose this construction in 1989. And in our proposal to the U.S. National Science Foundation, we said that we would build 2 generations of instruments, initial detectors or interferometers, at a sensitivity where if we were very lucky, we would see something, but we had to be lucky. And then advanced interferometers at a sensitivity where we would have a high probability to see a lot of waves. We had to do it in 2 steps because these detectors, these interferometers, are very complex. We had to have experience with a simple version of the interferometers before we could, with confidence, build the more complex, advanced ones. And so this was the original plan. The initial interferometers were constructed and then they operated for about 10 years, from 2005 to 2010. They could see colliding black holes out to about 300 million light years, but none have been seen yet, and interesting limits were placed on, on gravitational waves from colliding black holes. The advanced interferometers installation began in October 2010. And these are very complicated instruments. It required nearly 5 years to do the installation and then to turn them on and get them to begin to be working. The first one was turned on and began to operate as a full operating interferometer just 12 months ago. It is now within a factor 3 of design sensitivity. It's getting close to what we said we would do in terms of its level of noise. It's now 3 times better than our initial detectors. The second one will be at that sensitivity very soon, and we will begin our first gravitational wave search later this year. We will then continue to improve them, bringing them closer to their design sensitivity, reaching that by about 2017. And my prediction has been, ever since 2010 when they began installation, we will first see the waves about 2017, but it could be any time between 2015 and 2019. So we are entering this window where success is close. The technology is very interesting because in advanced LIGO, we are monitoring the motion of a 40-kilogram mirror to a precision of 10 to the minus 17 centimeters. That's 10 times better than what the numbers I went through with you. That is the level where the center of mass of this mirror behaves quantum mechanically. It's no longer governed by classical physics. It has a wave function, a Schrodinger wave function. That wave function is spread out by more than the accuracy of our measurement. So for the first time, when we reach design sensitivity, humans will see a human-sized object, a 40-kilogram mirror, behave according to the laws of quantum physics. We will see fluctuations, quantum fluctuations in where the mirror is. That meant that we have to develop measurements of techniques for measurements and for analyzing the data that will guarantee that these quantum fluctuations of where the mirror is do not get in the way of extracting the gravitational wave signal. Do not demolish the signal, do not destroy the signal that we are trying to detect. These are called quantum non-demolition techniques. And so we have developed those quantum non-demolition techniques. That was a major research effort in my own research group in the 1980s, and on in for part of my research group into the 90s and 2000s. And we now know how to do this. It's part of quantum information science. Other pieces of quantum information science are quantum computing and quantum cryptography. So three pieces: quantum computing, quantum cryptography, quantum non-demolition measurements. In preparation for multi-messenger astronomy, astronomers around the world have made collaborations with our LIGO project, written agreements for analyzing data together to search for the electromagnetic and neutrino signals that come out at the same time as the gravitational wave signals. One example is the Palomar Transient Factory on Palomar Mountain. It's another Caltech facility, that's why I describe it. There's a 48-inch telescope which looks out and searches for some source of light on the sky that changed very suddenly over a period of a few hours. It scans the sky and looks every few hours at the same place on the sky. It sends a signal of anything that changed suddenly to the 60-inch telescope, which automatically, this is all done automatically, it automatically then turns and looks at that source that suddenly changed, that star or whatever it is, classifies it, learns as much as possible with this larger telescope and with spectrometry on it. And that information, if it's really interesting, is sent automatically to the 200-inch telescope, but also to all the other big telescopes around the world where human beings go in and they look to see what this is, a human observer for the first time. And so this is the foundation then for doing the electromagnetic, part of the electromagnetic piece of multi-messenger astronomy. So I'm going to conclude now. This for me is an exciting time. My thesis advisor, my PhD advisor, told me back in 1962 that I should study geometrodynamics. Now I can do it. Now we can do it. We are getting theoretical insights from numerical simulations of colliding black holes, from analytical calculations. After we see something in the simulations, we can understand it and its details analytically. Our observational insights will come from LIGO and gravitational waves beginning sometime between this year and 2019. And there are a number of other venues, situations where we can study geometrodynamics. I've written some down here, but I've used up too much time, so I will stop at that point and take some questions. Thank you.
시간 관계상 요 뒤는 더 이상 이제 안 하시기로 했는데요. 질문 받기 전에 어떻게 제가 간단히 배경을 써마리하는 게 낫겠죠. 그래서 알다시피 오늘 얘기의 주제는 중력이에요. 중력은 아마 여러분들 알다시피 처음에 갈릴레이가 중력에 대해서 얘기를 했고, 그 다음에 이제 주로 많이 얘기한 사람이 이제 뉴턴이죠. 뉴턴은 이 만율력으로 중력을 설명한 것 잘 아실 거예요. 그러나 이제 그로부터 한 300년 뒤에 이 아인슈타인이 새로운 방식으로 중력을 설명한 것이 그 일반상대론이죠. 그게 1915년. 그러니까 지금으로부터 100년 전에 일반상대성 이론을 발표함으로써 새로운 중력 이론을 발표했던 거예요. 그래서 올해는 이 아인슈타인의 이 새로운 중력 이론, 즉 일반상대론이 100년이 되는 해로서 한국 물리학회에서도 많은 행사를 기획하고 있고 전 세계적으로도 많은 인터내셔널 미팅들이 준비되고 있어요. 그런데 이 아인슈타인의 중력 이론은 바로 중력이 아주 강한 경우에 적용이 되고, 중력이 약하면은 그냥 그 뉴턴의 그 만율력으로 적용해도 되는데, 실제로 중력이 아주 강한 곳은 알다시피 블랙홀 같이 중력이 강한 곳에서는 뉴턴 이론 가지고 설명 못하고 아인슈타인의 상대론 가지고만 설명이 돼요. 그래서 아인슈타인의 일반 상대론의 핵심은 뭐냐면은 중력을 자신의 특수 상대론에 맞도록 일반화시키는 것 하고요. 또 하나는 여러분들이 잘 알다시피 그 시공간이 굽어지고 뒤틀러지고 한 것이 바로 이 아인슈타인의 일반 상대론의 특징이에요. 바로 시공간이 굽어지고 뒤틀어진 것을 우리가 중력의 하나의 현상으로서 나타내고 있어요. 그래서 여기서 지금 킵슨 박사님께서 얘기하신 지오메트로 다이내믹스가 바로 이 시공을 기하학적으로 얘기를 하고, 그렇게 굽어진 것이 그냥 굽어진 뿐만 아니라 이거 실제로 물체가 힘을 받아 운동하듯이 하나의 다이나믹스를 갖는다 해서 지오메트로 다이나믹스라고 설명한 거죠. 그러니까 시공간이 그저 물체가 움직인 하나의 무대 정도가 아니라 이 무대도 같이 춤을 추고 연기하는 그런 배우로서 역할을 한다고 생각하면 돼요. 상당히 이제 어려운 얘기지만은 이것으로부터 이제 개념이 시작되고 있어요. 그래서 이러한 시공 기하학의 하나의 동력학을 설명하기 위해서 지금 이론이라든가 혹은 컴퓨터 시뮬레이션, 그 다음에 이제 이것을 실험하거나 관측하는 그 예로서 이 라이고 프로젝트를 설명을 했고, 중력파를 설명을 했고, 또한 블랙홀에 대해서 설명을 했던 거예요. 그래서 실제로 이제 주로 많은 얘기를 했던 것이 이제 이 블랙홀에 대해서 얘기를 한 거고, 제가 뭐 여러분들 다 이해를 하셨기 때문에 거기에 대한 자세한 설명을 안 드리겠지만은 실제로 오늘 내용은 바로 그 시공 기하학이 중력에 의해서 어떻게 굽어지고 뒤틀려졌는가라는 것에 대해서 주로 초점 맞췄고, 이것들을 실제로 구현하기 위해서 컴퓨터 시뮬레이션을 통해서 여러 가지 데이터들을 만들어 놔서 앞으로 이 라이고 프로젝트를 비롯한 여러 중력파 검출 장치를 통해서 나온 데이터들을 실제로 피팅하면서 이 킵슨 교수를 비롯한 컴퓨터 시뮬레이션 하는 그룹에서 만든 여러 가지 모델들, 아까 보니까 한 1000가지 이상의 조합을 해가지고 데이터를 만들어놔서 여러 가지 중력파형을 시뮬레이션 해놓은 거 있다고 그러는데, 만약에 중력파 검출 장치에서 뭔가 데이터가 나왔을 때 이 데이터가 이 중에서 어떤 케이스에 해당하는 건지를 거꾸로 역추적할 수 있는 하나의 검증하는 방식이 되기는 하죠. 그래서 이러한 내용이 이제 주로 되기 때문에 오늘은 뭐 제가 주인공이 아니고 킵슨 교수님이 주인공이기 때문에 제가 이 정도 서머리하면은 일단 배경에 대해서는 이해할 수 있으리라 보고요. 이제부터는 우리 킵슨 교수님한테 혹시 이제 궁금한거나 뭔가 물어보고 싶은 거 있으면은 자유로이 손을 들고 질문해 주시기 바랍니다.